James bonds. What are all those Jimmy bonds that quantum has? And let's start with this fellow so that we can put it in the right context. His name is Derek Muller, and he shows that molecules can be attached by a hydrogen bond. Okay, and so let's just quickly cover that base so that you know that that's the case. That's how it's being explained. That a hydrogen bond can bond two molecules, really one atom in each molecule, but it physically has these two molecules attached to them, or it could be atoms as well, right? Here it goes.
Rings of 8 sulfur atoms. Look for places to attach. They grabbed onto a carbon atom from a rubber chain, breaking its double bond and attached itself. Then with another free bonding site, it grabbed onto a carbon atom from a different rubber chain, breaking its double bond and linking the two rubber chains together.
So what's the point? The point is these are physical bonds, okay? They're binding, they're attaching, they're holding two molecules together. So we're not talking about an abstraction, okay? That's the point I want to make. And one of the problems we got is we don't see these bonds in the standard model. I mean, I've never seen a bond in there, a little line, dotted line or otherwise, right? So I don't know what all these bonds are, but it turns out there's more than just a hydrogen bond. And here's a summary of them. These are the James bonds, the Jimmy bonds, okay? We have all these secret agents that we know nothing about. One is a hydrogen bond, another was a covalent bond, ionic bond, and finally the metallic bond. Maybe they have another bond out there, another Jimmy bond running around for all we know. So what are all these bonds? Well, let's go through them kind of quickly here. Here's the covalent bond, okay? Let's start there. And you can see what it is. Really, it's the merging of shells, of orbitals, of energy levels. That's what they're merging. Here's the hydrogen, okay? And now we're going to have the oxygen there. And look, the two hydrogen molecules to build water, right? And they just merge their electron shells, their energy levels. And I thought an energy level was a region. What do you mean you're going to merge two regions? What does that mean? You're merging two concepts. So this is not an explanation, but this is the best they've got. And this is simply a description saying, the two regions merge, and because of that, you can find electrons in that region. And so what? How does that maintain the bond? How does that physically keep the two molecules, these atoms together? And they haven't explained that. They just say mathematically, that's what we verified, with math, that the electron shells, the energy levels merge. That's it. That's the covalent bond. Okay, now let's look at the ionic bond. Okay, here's the ionic bond. And how does this work? Well, one of these, the sodium and the chlorine, right, they lose their marbles. The sodium's going to lose its marble, right? The other guy's going to pick it up. And now because of that, one is charged, the other one is not. And so what happens is one becomes positive, the other one negatively charged, right? Because one's got one electron too many. And so the protons are now coming together, okay? Because one, or the atoms really, they're coming together. Why? Because one is positively charged, the other one's negatively charged. Okay, so what does negative and positive mean? What is this positive and negative nonsense? And they don't have an explanation for that. Again, this is just a description, a mathematical description saying, look, when this guy loses his marble, for some reason it becomes positive, the other guy becomes negative, and because of that, positive attracts negative, and that creates what we call an ionic bond. So now you know. Okay? See how easy it was? Yeah, this is not an explanation. It's not a physical interpretation. Okay, you haven't understood anything about the micro world that Mother Nature runs out there, because you can't visualize what they're saying. They're just saying the orbitals come together. Okay, so what's an orbital? Well, it's a region. You mean two regions come together and they merge and they keep the two atoms bound to each other? Regions are concepts. So you can't say, you got to put a physical object. They're not used to putting physical objects in physics, in mathematics, right? Physics, yeah, we are, but not in mathematics. And then here's the metallic bond, which is a sort of covalent bond, okay? And here you have an atom, right, one of those. And what they do, they have all these electrons running around for whatever reason, right? And they say it's just running around all these electrons. It's an electron soup, so to speak, right? And it keeps those atoms bound to each other simply because all these little marbles are running around. And again, if they're running around, how do they keep them together? And it's a kind of merging of the kind of like a mixture between ionic and covalent bond, where these atoms, these protons, right, the center nucleus of these atoms are attracted to others simply because all these electrons are running around. Okay, so that's it. We don't have an explanation of any of this. This is just description. They're saying they're running around because, if they're all discrete particles, you cannot talk about attachment or pull, which is what they're trying to describe here. You cannot describe pull, explain pull, if everything is a loose particle. That's why you cannot explain anything in Mother Nature's world, micro world, with particles. Particles are dead. And that's why good old Sean Carroll says, hey, we use fields. We don't use particles. Why? Because fields are supposed to be these extended objects. They think they're things. And so they say they extend forever through infinity. Oh, okay, so now we can talk about action at a distance through fields. There is no action at a distance, right? And they use this concept called a field to do the binding and the pulling and all this other good stuff, attraction, right? Okay, here's the hydrogen bond, the one we're going to talk about today. Okay, so here it is. These are the hydrogen bonds. And they put a little line there, usually dotted line. What is that line? I didn't see it in the standard model. I don't know if you've seen it. Please let me know. And they just put them by hand. They just say, oh, there's a hydrogen bond. What is it? What is it made out of? If it's going to bind two molecules together, there you have water plus NH3, right? Pulls them together and holds them together, the hydrogen bond. How does it do that? Two water molecules, the H and the O, are bound by, held together, right, by a hydrogen bond. So we're not talking about, an abstraction here. They're saying that this thing holds them together physically. Okay, so what is it? Please draw the stick. What stick is that? And where is it in the standard model? And they just say it's a hydrogen bond. That's it. That's all you'll know about a hydrogen bond. And they're going to try to define it, but again, using concepts. So, we don't need that. We need for them to point to that stick and say, this stick is a hydrogen bond, which is what they illustrate, okay? Okay, so here we have the hydrogen bond again, okay? That red one there. And so what do? Well, they go in there and they put a little dotted line. We say, well, what is that line? You can put anything you want in there. Well, what is that dotted line? And what we're saying is that this is what it is. It's a rope that connects one of the hydrogen that comprises oxygen, because remember, oxygen has 8 hydrogen atoms at least in it, right? And one of those balls, one of those fuzzy balls that makes up the oxygen atom, which is kind of like a molecule in itself because it's got 8 hydrogen atoms in there. One of those is connected to the hydrogen atom of another water molecule. That's what's happening, okay? And so that's our take on that. Here's another vision of that. Okay, you have the oxygen there on the left, and you have a hydrogen on the right, and we're saying that one of those hydrogen that makes up the oxygen atom, almost a molecule, you could say, right? Because it's a molecule in itself. But one of those balls is the one that's connected to the hydrogen on the other side. Yeah, so it's hydrogen versus hydrogen. That's all we have there. A single rope, and that's going to be the hydrogen bond. Okay, it's a physical bond. Is it attached? No, it's not attached. Remember that the 2 threads, of a rope, right? Here we have a rope, and the 2 threads, one forms the electron shell, the other one goes through the center and forms the proton star. That's encapsulated within, by the threads that make up the ball of yarn that is the electron shell. Okay, here we have water, okay, and you can see how, these molecules, they're running loose in that pool of water. And what you see is that what's merging is really the energy levels. That's what's merging. What is that blob that's around the two hydrogen atoms? And they say those are the energy levels. What they're blending is their energy levels. So that's kind of weird because energy levels are regions, and they turn them into physical objects at their discretion. When they define the atom, they say, well, it's the region where you can find the electron bead. The bead supposedly is the physical object. The region is only where you can find it. It's a where, not a what. And then they have all these wheres, and they merge and they blend and they form molecules. And you say, oh, did the region blended? What nonsense is that? And the electrons are running in there loose. Again, how does one electron affect another one if they're all discrete entities? And so that's when they say, well, it's got a field around it. What is a field? What is a field? A concept. Just a bunch of values saying, well, around it, it's got all these values. Yeah, it's a region of values. That's not a physical object. Okay, so here we have the covalent bond between two hydrogen atoms, and when they merge, they form that figure 8, typical figure 8, okay? Covalent bonding of two hydrogen atoms to form a hydrogen molecule, and they form that classical figure 8 pattern, okay? And the question is, what's happening there? What's actually happened in this covalent bond? And here we have an explanation from the rope model, okay? We say the two are coming together and they merge. Remember, the rope, as they come together, they become shorter and shorter and shorter until, one of the threads of the rope moves into the shell of an atom. The other one goes right straight through to the proton, to make the proton. So it's all made, the whole system is comprehensive in the sense that, you have a rope, and the rope gets shorter and shorter and shorter, and the rope makes up the electron shell as well as the proton star. When they come together, one simply unwinds into the other. That's what's happening there. So the blending of the shells has to do with the fact that, it's the same material. It's all done by this thread. It's a simple system in that sense that, it's all mediated by the threads. Okay, and what you see there, the ropes extending from each of the two atoms. Okay, every atom in the universe is attached to our two atoms there, our two target atoms that we're using there, right? Okay, so that's the model for covalent bonding. And here we have, here, let me put this up here. Here we have another version of that. Okay, that's essentially what's happening to the rope between them. Okay, that's our model. That's what we're saying is actually happening. Okay, simply the rope gets shorter and shorter until they merge into each other. And why? Because the shells and the protons are made of the same threads that make up the rope. Okay, so that's essentially our explanation for it. Very simple. I think baby stuff. It's just, you see it, you understand it, hopefully. I mean, I don't know, you might have questions. In fact, I'll open the place for questions in a minute here. And here's the final one, which is the ionic bond. And what is it? The shells are spinning. Remember, the electron shells spin around the nucleus. And one's spinning in one direction, the other one's spinning in the opposite direction. Okay, so one is going clockwise, the other one's, they're both going in the same direction, both going clockwise. So when one comes down, the other one comes up. And that's what the attraction is. It's a physical attraction between threads. And you have gazillions of threads swinging around. Remember, the shell is built out of every thread that comes from every rope in the universe. So you got gazillions of threads that build up these shells, and they're moving in the same direction. When one comes down, the other one comes up, and there's your attraction. That's what we call an ionic bond. Okay? That's why these atoms are attracted to each other. Okay? Very straightforward. If you can illustrate it, you can more or less understand it. You just have to follow. Now, do you believe in it? We don't care. Belief is part of religion, whether you believe it or not. Here we try to make it understandable so that you can look and say, I understand that. I don't agree with it. Or the other guy says, I do agree with it. That's belief. We can only show you the mechanism.